So it's time, let's start again with again a GStreamer talk about this time embedded State of the Union. Please welcome Olivier.
Hello, everyone. So this is a bit of a follow-up to Tim's talk for those who were there an hour ago. And but this time I'm going to really focus on what's new for embedded use cases. So first, who am I? Quick introduction. My name is Olivier Crête. I've been a GStreamer contributor, developer for 12 years now. At Collabora since 2007. First, I started doing video calls on using telepathy for the MeeGo MIMO platform with Nokia. And since then, I've most diversified to basically everything that you can do with GStreamer, from video editing to embedded systems to transcoding cloud systems. But a lot of the work that I've been doing in the last couple of years has been on embedded systems. So this is why I'm going to talk about them today. Just a quick introduction. What kind of embedded systems use GStreamer? And the answer is a lot. Everything that does video, audio, and embedded systems, you will find GStreamer in many, many, many products there. Sometimes we're really surprised to find them. So for example, in the TV space, it's pretty big. On my slide, you have some LG TVs, some Samsung TVs. A lot of these actually have GStreamer on the inside, on the smart side. On the top left, you have the Xfinity box from Comcast. For those who are not from America, Comcast is the biggest cable company in the world. And every set-top box that they ship is Linux box with GStreamer for all the playback. And then there's a bunch of others. Bottom left, it's UView, which is a British company. More set-top box. So a lot of the TV space has it on the endpoint, but now actually a lot of recently it's been growing in the production side as they've been transitioning from hardware and FPGAs to software-based workflows, and GStreamer has seen a lot of traction there. In-flight entertainment is another big one that people interact with all the time. So in a lot of planes, almost all the planes, modern planes these days, by modern I mean from the last 10 to 15 years, you go and the in-flight entertainment, every time you play a movie, that's GStreamer. Even in the space station, this is a really cool one. It's one of my favorites. I show it every time. It's a little camera that floats inside the space station made by the Japanese space agency, and that has GStreamer inside. So I spoke about these, but there's also a bunch of other devices like security cameras. A lot of the high-end ones have GStreamer on the inside. Yes?
Could you elaborate on what version of GStreamer? Is it 0.10 or 1.0?
Where?
In all the embedded devices?
So it depends. All the new generations are 1.0 generally. Like the ones that fly in the sky, in the planes, these are probably from 10 years ago. So that's probably whatever version they deployed in the very past. But for example, this is 1.10 something. Yeah, it's pretty recent. Smart TVs, some of them are actually quite like the Comcast guys are on 1.14 as far as I know. So a lot of these actually they keep up because they want to deploy new features, right? They need the newer dash and the newer HLS features, so they have an incentive to keep up. And they have like rapid deployment and all these things in this industry now. It's not like, especially in the TVs and the cable operator, they really want to deploy new features very quickly. So I was saying there's all of these, but there's also a bunch of others, like other industrial equipment also that you don't think about, but they process video in there. And they use GStreamer very often because it's on many embedded chips. When you buy them, GStreamer is the framework that comes already working. If you buy a Xilinx FPGA that have a video encoder there, well, the framework that Xilinx enables is GStreamer. So it's the quickest way to get a working product. So I'll give a little summary of the things that we have done that Tim hasn't covered that are really specific to embedded. First, a lot of work has happened again this year around video for Linux codec support. So Video for Linux is the Linux kernel API that is used for things that have a queue. So video encoders, video decoders, amongst other things, displaying things, capturing from a camera, some display devices, some other video processing devices, scalers, and things like that that are not in the display path, that are used in memory-to-memory mode. So there's a lot of these, but a big part is video encoders and decoders. In the last year, we've merged the HEVC encoder and decoder support. We have a JPEG encoder, a plugin, and a VI codec, which is kind of interesting because it's not a useful codec at all. It's only to be able to test the kernel infrastructure. So it's a fake codec that is implemented in software in the kernel to be able to test the whole codec infrastructure inside the kernel without having to deal with the actual hardware. Another nice feature that, especially on the camera side, some cameras took like seconds to probe because we enumerated a bunch of things that we didn't really need to enumerate. So Nicolas has done a lot of work, and now the device probing is instant on almost all hardware. So you can get the list of all the devices and the relevant capabilities. Last year, I talked about stable element names for encoders and decoders. So originally, for video for Linux elements in GStreamer, we were generating a new element name every time a device would pop up. So we would connect a new camera, and a new element, a new camera, a new encoder in your phone, and the element name would change, would appear with a new name, and which means that on some embedded system, every time you reboot it, the element would have different names, which is good, which is okay if you're using like Playbin and it's a auto-generated pipeline because you don't care about the name. But if you're doing pipelines by hand, it was a bit annoying. So now we have these still, but we also have a set of elements that have static names, and then you give it the device so you can control it more manually. So we had this for encoders and decoders last year. This year we've also added the same thing, but for transformation elements. So transformation elements are things like scalars or color converters or different elements that normally convert raw images into different formats. One thing that is being discussed that's not there yet because the kernel is not there is having good support for stateless codecs. So most codecs that people traditionally use on these embedded hardware, you would just give it the H.264 bit stream, and it would give you a decoded stream. It did the whole parsing of the bit stream and everything in the hardware side, which was often just firmware running on a different chip. But now the new trend is to make the hardware cheaper by moving all of this parsing onto the CPU side and by doing it in user space and software. So you need slightly different APIs in the kernel. There's a lot of work happening with the request APIs in the kernel to do exactly that, and GStreamer will support it once it's there. This is something actually we've been actively working on. Completely separate subject now. We've merged a plugin called IPC Pipeline, which I like to talk about because I think it's really cool. And it allows you to split a pipeline into multiple processes, but have a single, the master pipeline controls all the others. So for example, the typical case is that you have one process that talks to the network that downloads the dash stream from the internet that is exposed, and then it passes the data to another process which actually talks to the hardware decoder. So you can separate the hardware decoder, the part that, and these are often not as secure as you would like. They do a lot of bitstream parsing and things like that. So you want to make sure that this part that might be compromised by an invalid stream is not connected to the network and vice versa. So we can actually split the pipeline in multiple levels. I have one stage that talks to the network, one stage that does the parsing, and then a separate stage that talks to the hardware. And this is also useful to implement DRM, sadly. So, but it allows really you to have multiple levels of security. And it's right now, it's not you have to create everything manually, so it's not like automatic at all. Right? You have to actually create your pipeline manually. But for these kinds of devices, you actually want to control exactly what happens and what process and everything. Another completely separate thing, we've implemented a new mode of interlacing that actually exposes how some of the hardware works. So traditionally, in interlacing is that you have one frame in traditional analog TV. You have one frame that contains every odd line, and then the next frame, which is the next field, contains every even line. So instead of having 30 frames a second, you have 60 fields. And these fields are really half the frame, one odd, one even, odd, even. And when these come to digital, mostly what you did is that you put both of these fields in the same file, in the same frame, in the same buffer, right? So you have the odd lines, the even lines are taken at slightly different times. And this is why when you look at it like without properly deinterlisting it, you'll see a jagged image. This is the traditional way to do it. Some hardware, NH265 actually, do it in a different way, is that you actually have the fields separately in separate buffers at separate times. This allows for a bit lower latency. So you can have like, you don't have to wait for both fields to have been captured to start processing the first one. And we've implemented this for GST-OMX and actually throughout the GStreamer framework. We've done also a bunch of work to reduce the latency in RTP pipelines. When we actually try to measure the latency of the actual data, we realized that the latency that GStreamer claimed to have was not really true, that there were a bunch of little bugs all around the different elements that actually made the data stay in there longer than it should have. So we did a bunch of little bug fixes, and now you can actually push buffers with the latency that it claims to have, which can be almost zero if you're not doing anything that any queuing. We also done a bunch of work in the GStreamer OpenMax elements. A lot of this is for the Xilinx Zinc MP platform. We fixed a lot of bugs. We've added support for 10-bit video formats for HDR. We have a lot more DMA buff and zero copy modes so that you can connect them in different ways and have one side or the other do the allocation depending on what's better for your specific use case. We've had the region of interest. This is a really cool one, I think. Basically, it allows the application to say, in my image, this bit is where the really important thing is, so put more bits there when you compress. For example, you can have a face recognition algorithm that says there's a face there. So in my video, everything else is not that important, but the face has to be recognizable, or the car plate, or things like that, or the subtitles. If you have subtitles burned into the video, you might want to put more detail there so that the text is readable, even though you really compress the rest of the video a lot. Another little thing is a dynamic frame rate in the encoder. So now the encoder, if you change the frame rate, it doesn't reinitialize everything. It just changes the frame rate. So you can change the frame rate really quickly. Another nice thing, we've done a bunch of little improvements on the DMA buff support. One of them is that now we do explicit DMA buff synchronization. It turns out that the Linux kernel, when you use DMA buff buffers, when you access them, you actually need to tell it, I'm going to access it, and now I'm stopping accessing it, so that it does the appropriate cache invalidations. Otherwise, you get corruption, especially on Intel hardware, which is one that actually lots of people use. And we have a direct GL DMA buff uploader. So traditionally, when you would import a YUV image, you would have to use a shader to convert it to RGB to be able to be put on the display. But some hardware, in particular Vivante in the IMX6, they can actually take the YUV and display it directly, entirely in the hardware. So there's a direct uploader now that bypasses this shader that does the conversion. So these are the things, a bit of a summary of the things I found by looking at the Git log and trying to remember what happened in the last year. These are some things that are actually being worked on more or less actively. But these are things that I think are kind of interesting. There's been a lot of activity around neural networks in GStreamer. Neural networks are all the rage this year. And a lot of it is to process video, to recognize things in video. And GStreamer is really good with video. So we have, for example, NVIDIA has released something called the Deep Stream SDK that works both on embedded Tegra and on the cloud side, and that uses CUDA to do the actual neural network processing. But all of the video elements are actually using GStreamer. This is largely proprietary, sadly, but the GStreamer, actual GStreamer is not. But all of the interesting bits that NVIDIA has done is using their proprietary things. But there's also a couple open source projects that have been released. There's one called GStreamer. There's something called GSE Inference that's meant to be released next month. They promised to do neural networks with GStreamer. So I expect that in the next year or two, we'll probably have something upstream that everyone can collaborate on to integrate neural network frameworks with GStreamer. Another thing that's coming up now is different companies are coming up with specialized hardware. So instead of using GPUs, yes?
Do you use TensorFlow? Do you use TensorFlow?
We use TensorFlow. Say a lot of these frameworks actually integrate TensorFlow or TensorFlow RT with GStreamer. That's like the main one. But I know some people are actually using other frameworks too. Yes. So yes, also specialized hardware is coming. Like so, a lot of these they are like specialized accelerators that are not like GPUs, but that have been really designed for AI workloads. And these will require some integration, and GStreamer is probably going to be a key thing there. Another branch that we have not merged in a long time, but I have promised to review, is Android Camera2 API. So this is the new camera API that Android has had for a couple years now, and that is completely more modern than what we're using right now. This new API, it's exposed in the NDK, so you can use a native C API to access it instead of going through Java and going back to the C++. It does things like where you can like record a video and take a picture at the same time. It allows you to capture multiple streams at the same time, like the front camera and the back camera at the same time on some phones, etc. And to have all the modern features that your your camera application has in your phone, they're all exposed through that API. So there is a plugin in the GitLab that is meant to be reviewed, and hopefully we'll merge it in the near future. There's also been a bunch of work about remote tracing. So GStreamer has a tracer framework that allows you to write tracers to trace things, and these are especially nice to find performance bottlenecks, figure out what exactly is going on in the pipeline when it's running. And now there's some interest to do it remotely, so to have some infrastructure to forward this information to a separate computer. So you can have the tracer running in your embedded device, but have a nice UI on your computer to know what's going on in my pipeline and why are my frames being dropped, even though many indicators say they shouldn't be, right? So where's the bottleneck? What is the bug? What have I been doing wrong? Another next step that we're going to do, that we've just switched to GitLab, where we gain amazing new technologies, such as doing a build before you merge the branch, and not after, and running tests before you merge instead of after. And in this move, we've right now we build for Linux, x86-64, we build for Android, and we build for Windows. And we would really like next to build for an embedded platform to reflect where GStreamer is most used. And the next step after that will be to actually run tests on an embedded platform. We've built a prototype using a Raspberry Pi. And the prototype used Jenkins and Lava. So Jenkins to do the build and Lava to actually run on the device. Our goal would be to replace Jenkins with GitLab CI here, so that we can actually integrate it nicely in our CI. We have a vague plan on how to integrate GitLab CI with Lava, but I don't know if anyone else has already done it, so we actually have to see if it works. To use the GitLab CI APIs to drive Lava and have all the details together. So this is basically what I had to say. Do you have any questions? Yes? Yes, you.
So when do you think all these things that you I'm curious when all these new things will come to NVIDIA SDK for Jetson.
So the NVIDIA part is already there. It's called GStreamer SDK. It works on Jetson and on the whatever the server ones are called.
And this point of interest too?
No, a point of interest is that, as far as I know, is only available on Intel and Xilinx.
So, but
So it needs support in the you need support in the encoder. I don't know what the NVENC API can do.
So, but at the end it will be in all platforms, hopefully. In few years it will be everywhere.
Well, yeah, but especially this region of interest thing, it really depends on the actual encoder implementation. So I don't know what they have in their implementation.
And I have another question, but maybe later.
Yeah, go for it.
Other questions? Yes.
I have two questions. You mentioned before this IPC pipelines to create. There's another plugin called Interpipe, which allows to make a separate pipelines and link them together. What would be advantages of this one over that one?
So the main thing that IPC Pipeline does differently from Interpipe is that IPC Pipeline actually controls the pipeline entirely. So when you do you put the master one in the pause state, it put all of the other ones in the other processes also in the pause state. So the control is unified. While Interpipeline, kind of the point of it is that it's the other way around. They're really separate. So you have a sender and a receiver, and you can stop, let's say, stop the sender and change it, and stop the receiver independently. Well, IPC Pipeline is really meant to have things that to the application appears as a single pipeline, even though other bits might actually be separate in separate process.
If I would want to build like
Your microphone.
If I would want to build very dynamic application where I create the parts of the pipeline at the runtime, which one would you recommend to use?
So if it's like, if you want to stop and start different pipes, like the inter video source, sync source, and the inter pipeline, whatever it's called, interpipe, yeah, is pretty more suitable. In IPC pipeline is more traditionally meant for like playback cases where you want to separate things, but it's not because you want them to run separately, it's because you want them to actually appear as one thing to the application.
And the second question is more on the embedded side of it, but the same IPC.
Yeah.
If I'm using like very low powered IMX6 CPU, and I have some hardware source of video, if I would split my pipeline in parts, how would it pass the buffers between the pipelines? Would it be like a mem copy, and it would be big performance hit?
So right now, IPC pipeline, it's a socket. So actually copy everything through the kernel. For the use case that we're looking at, it was fast enough. But I had the plan to actually pass memory buffers using either passing the file descriptor or shared memory, but we never implemented it because it was not required for our use case.
That would be useful.
Yeah. Yeah.
Last question. Yeah.
A question regarding the debugging tools. Are you actively working on it, or is something already available?
So there is something available from the guy from Samsung. I can't remember the name of it. It's open source. It's on his GitHub. Does someone remember the name of the thing that Martin worked on? Huh? Yes.
Oak Tracer.
Oak Tracer, yeah. So that's one of the efforts. I would like to see it more integrated. Right now, you need to patch things to actually use it live.
Okay, thank you, Olivier.
Thank you.